Good morning. We're going to get started. My name is Joly Reidenberg. I am the academic director of CLIP here at Fordham and a visiting professor this year at Princeton Center on Information Technology Policy. Welcome to the conference. This is CLIP's 8th annual Law and Information Society Conference. And this year, we're very pleased that Princeton's CITP is co-sponsoring the sessions with us. We'd also like to thank the Internet Society, who is streaming today's conference live. Our theme today is the Internet of Things, and more simply understood as Internet-connected objects. As we're exploring the sessions this afternoon, how network connectivity really offers some amazing opportunities to facilitate and improve our daily lives and even our health. At the same time, the connected objects in our daily life raise a host of legal, technical, policy, and social issues. And we've constructed the program today to really try to capture all of these dimensions. In a moment, I'm going to ask Ed Felten from Princeton to come up and say a few words and then lead us into our first session. But I'll run through a little bit how we've thought about the program. We're starting the day with a panel of technologists to show us some of the things that are coming down the pike, some of the applications of connected objects. Then our next panel will take a look at some of the security issues that they raise. We'll follow that, addressing a scope of regulatory fields that will be intersecting with smart objects. Then we break for lunch. We have a keynote address by FTC Commissioner Julie Brill. Following lunch, we'll have sessions on connected health, and then I'll call it connected fashion. It's really looking at how smart objects are being used in the merchandising world with a focus on the fashion industry. And our conclusion this afternoon before a cocktail will be reflections in the form of a fireside chat with judges Denny Chin and Marilyn Patel. The format is designed to be very informal, so our speakers are only going to make very short opening remarks, and then we've designed it to be really discussion with the panelists and a lot of question and answer with the audience. So let me just say a couple of words on logistics before I turn things over to Ed. If you're getting CLE credit, be sure that you both sign in and then sign out. We know there's a connectivity issue with the Wi-Fi, and hopefully by the break we will have corrected access information, but we'll certainly get that up and running shortly. I would be remiss if I didn't do a series of thank yous for the conference, because no conference like this can take place without a lot of people putting in a tremendous amount of effort and really making things happen. On CLIP's end, I really want to express an enormous debt of gratitude to Cameron Russell, our executive director, who's really put so much of today's program together. Tom Norton has been helping tremendously with our logistics, and we have some of the student staff members of the Intellectual Property Law Journal helping throughout the day. It wouldn't be possible without our funders at CLIP. We have a series of benefactors for our center who are listed on our webpage, and also the Waxberg Chair has provided support for today's conference. So with that, let me turn it over to Ed Felten from Princeton, our co-sponsor.
Good, thanks. Thanks. First, let me join Joel in thanking everyone who's helped make this possible, especially our hosts here at Fordham, Joel, Cameron, and Tom, for everything they've done to make this work. So thanks very much. Okay, so I would like to give a brief tutorial and perspective on the Internet of Things from a technology standpoint. I won't talk for too long because we want to get to the fun part of this session, which is demos of Internet of Things projects built by two of our Princeton students. And you'll get a chance to, Bonnie Eisenman and Dale Markowitz, and you'll get a chance to talk to them and see their projects as well in the break after this. Okay. So when we talk about Internet of Things, we're talking about, of course, objects that are smart and networked. But it's kind of a commonplace that more and more things are getting smart, having computation built into them, and being networked. And so I want to not just repeat that, but talk a little bit about why this trend is especially interesting and some of the aspects of it that might be unexpected. Let me start by talking a little bit about Moore's Law economics. Moore's Law is commonly stated as saying that as being about the rapidly dropping cost of computing technologies, that the cost falls 10 times every 5 years. That's not exactly what Moore said originally, but nonetheless, this is the received wisdom as to what Moore said. This is really an incredibly transformative change. To give you an idea of how rapidly this changes the economics, we can look at one measure of computing power, the cost per million floating point operations per second. It doesn't matter exactly what this is. Think of it as a measure of how much it costs to get a certain amount of computing power. In 2003, that cost about $100 for that amount of computing power. 10 years later, in 2013, 12 cents. So really what Moore's Law economics is about the kind of transformation that takes something from costing $100, meaning that you're not going to build it into an everyday object. But if it costs 12 cents, now you might actually build it into all kinds of devices. So Moore's Law economics means that there's this kind of cost ceiling on the cost of, there's a kind of cost ceiling on the, as to what it costs to make a device smart, but that cost is falling at this incredibly rapid rate. And so more and more devices become viable to be made smart as that cost goes down. Now, Moore's Law economics applies to general purpose computing and networking devices. What that means is that rather than taking a device, if you want to make it smart, and building in a kind of a limited form of computation or a limited or specially designed form of networking that just does what that device needs, if you want to ride the Moore's Law curve, you have to be building in general purpose commodity devices. And what that means is that general purpose devices are both cheaper and more capable than special purpose devices. And so what that means is that a smart device is going to have a networking capability and a computing capability that's much more general than you might think it needs in order to have the kind of brains you want to put in it. And that's both a blessing and a curse. It's a blessing because innovative people can come up with clever new things for this device to do, and they can be downloaded as new software into the device at any time. And so new functionality can come along, and the device can grow, and these devices become platforms for innovation. But it's a curse because malicious people can come up with new things for the devices to do, implement them as software, and arrange for that software to be installed on the device. And so both the functionality and the platform nature of this and many of the security risks and the potential problems flow from the fact that they're built using general purpose computing technologies. Okay, now Moore's Law economics applies to all the things that are in these devices, computing, storage, and networking being the obvious one, but the one that's maybe a little bit less obvious is sensors. And so I'm going to focus a little bit on the role of sensors in all of this. Sensors are simply anything that measures something that's happening in the world. That might be something like a camera, a microphone, or a seismometer, something else. So let me talk a little bit about sensors, and I'll use an example here of an accelerometer. This is a very simple sensor, which you might think doesn't do that much, but I want to talk a little bit about, give you a little bit of intuition about how an accelerometer might turn out to be useful. So first of all, what is an accelerometer? Well, here's conceptually a very simple accelerometer. It's a box, and it has inside of it a ball with springs on 4 sides. And so the ball is kind of hanging in the middle there, suspended and held in place by the springs. Okay. And now what this can do for, now this is a simplification of a real accelerometer. A real accelerometer would be 3-dimensional and a lot smaller, implemented in a different way, but this is kind of the concept. right? So you have a ball on springs inside of a box. So what does this let you do? Well, this, it turns out, lets you measure when somebody pushes on the box. Suppose that somebody takes the box and shoves it to the right just a little bit like this. Boom. All right, so the box moves over to the right, and it might not be obvious, you haven't studied physics, but in fact the ball stays in place as the box moves. Then the springs will push the ball back to the middle. Okay, now imagine that you had a ruler attached to this thing, and you had a clock, and you could actually watch the movement of the ball within the box. And so what you observe is, at the beginning the ball's in the middle of the box, then suddenly the ball's over to the left a little bit, and then the ball moves back into the middle. Right? So that, the measurement, the observation of that movement of the ball tells you that somebody must have shoved the box to the right. And if you measure exactly how far it moves and exactly how long it takes to come back and so on, you can figure out exactly how far they shoved it to the right and exactly how fast. So you can figure out how the box moved. And in fact, anything that pushes on the box, without anything that moves or pushes on the box can be measured this way. You can measure the exact force that is being exerted on the box at any time. All right, so who cares about that? Well, once you add software that is able to take those measurements and make inferences from them, you suddenly get all kinds of interesting capabilities. For example, there's a force that's always pulling on the box. It's called gravity. So here's my phone, right? Gravity's pulling on the phone, and I'm exerting a force on the phone to push it up. The accelerometer in the phone is measuring that force. What does that mean? Well, gravity is a force, you know how strong it is. You know that, that gravity always pulls down, and the counterforce always pushes up. So that tells you which way is up. So the device knows its orientation, and that's how your phone knows to rotate the display when you turn it. But now imagine you ride in an elevator. Well, if you've ridden in an elevator, you know that when the elevator starts moving upward, it feels like gravity is stronger. Then if gravity feels normal for a while, then when you're slowing down at the top, gravity feels like it's less than normal. Well, your accelerometer can tell that. It can tell, gee, gravity seems to be pointing in the same direction, but stronger for a little while. Then it goes back to normal. Then it's less than normal for a little while. Measure how long, how much. You can figure out, gee, that person must have ridden up in an elevator. And here's how fast the elevator was going. Here's how long they rode. Oh, maybe they went up to the 12th floor. All of that from that simple ball and springs and a ruler and some software. Then you go for a walk. Well, you might have the accelerometer on your phone that's in your pocket. And as you walk around, you kind of bounce up and down a little bit with each stride. The accelerometer can measure those bounces and figure out he's taking a stride now, he's taking a stride now, he's taking a stride now. And it can get an idea of how many steps you're taking, how rapidly. Are you walking or running? Are you turning? All of that from a ball and springs and some software. So the sensor plus software can be a very powerful thing. Even a very simple sensor can give you a lot of information about what's going on around the device. Now, if you look at a mobile phone, a state-of-the-art mobile phone, this is a Google Nexus 5. As an example, it has a lot of sensors in it. It has 2 cameras, a microphone, a GPS, it has a gyroscope, an accelerometer, a compass, it has a proximity sensor, something that senses the amount of ambient light, it has a barometer in it to measure the air pressure, and it has a magnetic sensor, a so-called Hall effect sensor. All of these things in the device, in a commodity phone, and controlled with software. That means the device can tell a lot about what's happening around it in the world as it's operating. So the design of Internet of Things devices, a lot of it is about combinations of these things, of computing, of networking, of sensors, to try to make a useful service. So let me give you an example of a custom device which uses these technologies. This is a Fitbit Flex. I have one here on my wrist right now. You wear it on your wrist. It has inside of it an accelerometer and a computer, and it can network to nearby devices. And so it measures what you're doing. It measures strides. If you wear it at night, it will give you a graph of your sleep. Here's a graph of my sleep last night. You can see I slept very efficiently last night. It tells me when I woke up, when I rolled over, when I went to bed, all these sorts of things. So if I have a night where I don't sleep this well, I'll know it. I'll be able to tell when I woke up and learn some things that I wouldn't otherwise know. And so just by having this thing, this accelerometer attached to my body last night, I was able to do that. Now, This is kind of capability is something which today many people have in dedicated devices, but there's no reason it can't be built into your shoes. Shoes are not that expensive, and when you think about the cost of the basic computing, networking, and sensors you need for an Internet of Things kind of system, you could quite easily build this into your shoes. So you should think about shoes and other everyday devices getting smart, getting sensors, measuring what's happening in the world, and this shoe can both track my exercise, how active I am, and also try to be a better shoe by figuring out, gee, it seems like he's walking on gravel now. Maybe I'll change the way the padding in the shoe works. But it's not just shoes. As the cost curve comes down, you need to think about other kinds of objects, maybe taking on smart capabilities as well. It's not out of the question to think that pencils will, before too long, be smart. So what would a smart pencil do? Well, it would know when it needs to be sharpened. It would know where it is, so you could find one. It could warn you that you're about to leave to go take the SAT and you only have 2 number 2 pencils with you. Probably much more usefully, a pencil with an accelerometer on the end could figure out what you're writing. Because as you write, the top end of the pencil is moving around opposite to your motion on the paper. Contact with the paper could be sensed as a kind of small jolt. And a smart pencil could quite easily make a diagram of what you're writing and upload it to you, make it available to you some other way. So what we're really talking about here is the Internet of Everything and the opportunities that become available when everyday objects become smart. And there is an active industry, of course, trying to build these things. There's also a pretty active community of hobbyists who are building interesting and fun things. This is part of the so-called maker movement that is quite big at the moment. People building interesting objects using commodity Internet of Things technologies. And you know that it's a real trend because it was on the cover of Wired. So let me give you a few examples of the sorts of technologies that are used for this, and then I'll turn it over to our students who can talk about what some of the projects they've actually done by using these technologies. So this is an Arduino board. This costs about $20, this particular one. And this is one of the older, larger Arduino boards. So how do you use this? Well, you can, it has a USB port which you can use to connect it to your laptop. So on your laptop, you can write a program that tells this thing what to do. You can connect it by USB to the USB port in your laptop. You can download the program into it, and it will do what it does. But importantly, it has at the top and bottom these little black things here, which you can use to plug in wires. And these wires can both be attached to sensors, and there's a big catalog of sensors you can buy to connect to this thing. It can also be connected to actuators, things that do things in the light up lights or turn switches on and off or other sorts of things, to make the device do things. And so if you have one of these, if you can provide power to it, either by plugging it in or by putting a battery pack on it, you can download code into it, hook it up to some sensors, and you can just sort of in your kitchen make an Internet of Things kind of object. This is, as I said, this is an old Arduino. The newer Arduino devices, like the Trinket, this one costs $7.95. It's cheaper in quantity, and you can see how big it is. We actually have a couple of these. You guys pass those around, please, if you want to take a look at them. This is the kind of part that really makes it possible to build all kinds of interesting devices. It's quite small, doesn't use much power, very cheap in quantity. This thing is a little bit higher end. This is called a Raspberry Pi. It's about the size of a credit card, and it costs about $35. And this is a real computer. When I say a real computer, I mean you can hook it up to a keyboard and a mouse and a monitor. You can log into it. It runs the Linux operating system. It has a network port. It has a USB port, and pretty much everything you'd expect from a real computer. But it costs $35, which means that you can put it in places and build it into projects that you wouldn't have been able to do before. And remember, Moore's law applies to all this stuff too. Along with all of this, there's a very active little industry of of people and companies who make and sell things. One of the best-known companies in that area is Adafruit, which is right here in New York. And they have this catalog. They have all kinds of tutorials. They'll sell you all kinds of things. And to give you an idea of the size of their catalog, here's one section of their catalog, just for things that go with Arduinos and similar objects. So 64 kinds of batteries and power supplies, 78 kinds of cables, 6 kinds of lasers, 70 kinds of displays, 177 kinds of sensors and parts, 14 solar things, presumably for solar power, wireless connections, 26 of those. It's a big catalog, and you can shop, you can do the tutorials, and you can build up a nice little workshop. And some of our students have done that. They built a maker space in our engineering building, and we have a growing community of people on campus who are doing this. And of course, you may remember this is pretty much what happened with personal computers before they became a big industry, is that there was this kind of hobbyist community building a lot of interesting things. Okay, so let me turn it over now to two of our Princeton students. First, Bonnie Eisenman, who's a senior, and then Dale Markowitz, who is a junior, and they will demonstrate projects that they've built. Don't think that these are the only things that Bonnie and Dale have ever built. I think Bonnie especially builds a new project every week. But these are just examples of the kinds of things that can be done by a person who is very smart and creative, but doesn't necessarily have a lot of resources or time to devote to a project. So first Bonnie.
All right. Hi, my name is Bonnie Eisenman. I'm a senior studying computer science at Princeton University. All right. So I wanted to build an Internet of Things object. I was thinking, okay, what problems do I have? What problems do college students have? Well, obviously sleep. So I have a pillow here. It looks pretty normal, except for the fact that there's this USB cable hanging out. There actually would not be a USB cable except my battery pack broke last night, following the rule of demos always go wrong at the last minute. So what this does actually is it tracks my sleeping patterns, much like the Fitbit does. The difference is that the Fitbit costs $100, and even though I don't get any quantities or any discounts for mass producing anything, I managed to do all this, I think, for somewhere around $25. So I'm going to plug it in. All right, so there's essentially a touch sensor in here that's just a giant swatch of fabric that can detect human touch. It also detects pressure. So I'm getting these numbers in. It's actually communicating wirelessly to my laptop what those numbers are. So that's great, right? When I sleep, my head's on the pillow. So I whipped up this tiny little interface. So I can actually track my sleep each night just by plugging my pillow in. And so here, for example, let's see. Yeah, so there, for example, is data I got from my sleep last night. So the numbers that it's sending are just based on, how much contact do I have with my pillow. So the numbers themselves aren't so interesting. What's interesting is the patterns that you can figure out. So for example, it looks like I woke up briefly at 2 a.m. last night. I can also tell that I appeared to have certain REM cycles where I had plateaus of activity where I didn't appear to be moving. So obviously I can't, so you can take that data, you can do interesting things with it, you can figure out, okay, what's my sleep patterns like? So this is really just a proof of concept of, okay, I managed to build this pillow during midterms week in my free time, right? So that's fun. But what if I, for example, made it communicate with my phone? So it's using Bluetooth, which means that I can just, write a phone app. Maybe I can write a new alarm clock that only stops ringing once I actually get out of bed. Or things like that. Or maybe, like this, for example, this is a website, right? I can go to my doctor and I can say, hey, look, here's my sleep data. I seem to have issues sleeping. My Ambien isn't working, things like that. Yeah, so that's mostly what I have today.
Thanks.
Yeah.
And there'll be a chance to talk to Bonnie and Dale and see their projects up close during the break. So next, let me introduce Dale Markowitz, who is a junior at Princeton.
So I decided to build today a small lamp called the Things to Get Done-O-meter. And right now it's glowing red. And the idea is that on my phone, I have a to-do list app called Listacular. And I basically put in whatever task I want to do for the day. And the idea is that my lamp is glowing red because I haven't done any of the tasks. But as I start to check them off, it should tell me that I'm less in trouble. Let's see if it does. Ah, yeah, a little bit better. And it goes on this spectrum from red to green, the more tasks that I do over the day. So let's see. Just finished up most of them. Let's see this. And is it a little bit more green? Yeah, a little bit more green. So yeah, this was pretty easy to make. It's plugged into my computer right now, but that's actually just because I was worried about getting it connected to the Wi-Fi, but actually it works over Wi-Fi. So the idea is that I would put this in my room, and then if it's red at night, I realize that I shouldn't go to sleep and I should actually finish up my tasks.
Can you come up on? Okay, we have a little bit of time for questions, either for me or more likely for our student demoers. But first, I actually want to ask you guys to talk a little bit about the technology that you used to build this, how long it took, and so on.
Yeah, so for mine, I'm using an Arduino Uno, which is what you showed on your slides. So those cost about $20. You could probably shrink it down to use one of the cheaper ones, though. There's a Bluetooth module, and then there's, I can show it to anyone who wants to come up here, there's just some conductive fabric inside, so that cost about maybe $3. And so then to program it, I'd worked with stuff that did touch sensing before, in a class at Princeton, actually. So that part was easy. I figured out that I could get touch sensing working even through the pillow fabric, which was exciting. And so I think I spent under 10 hours on it.
I've just sort of decapitated my lamp, but if you can see here, I'm using one of the smaller Arduinos that Professor Felten was talking about. It's about 20 bucks. And this is a really simple setup. Oh, so I should also say, in the lamp is an LED strip, which has 3 color controls. Overall, the project was really easy to build, definitely under 3 hours, I think. And basically, I learned about electronics because actually, electronics is what got me interested in coding in the first place because, web apps are cool, but making physical things seemed a lot cooler. So definitely not difficult to learn because that's how I learned how to code.
Do we have questions from the floor? Wait, yeah. Well, he wants to buy them both.
Ooh, exciting.
Yeah, sorry. So let me repeat the question. The question was, how can I buy these? Well, you could maybe you could talk about how something like this might turn into a product.
Right. So I guess if there's actually a couple websites that let people like us sell our homemade electronics things. I think it's called what is it, Tyndall? There's a couple different websites. Personally, I don't sell my things. I'm doing this for fun. But there's definitely people who use these as prototyping platforms, figure out what they need, and then take them to market, make their own custom materials, cut the prices by half or whatever.
Yeah, definitely. Actually, so the Arduino, which is inside of both of our projects, I've actually heard is what Fitbit uses to do their prototyping. So, yeah.
Yes.
Can you hear me? Okay. How would you go about building privacy or security features into these devices if you were concerned about somebody, hacking into them and seeing how you were sleeping and whether you were accomplishing all of your tasks?
So that is a great question. I did not build any security into my pillow, and I was thinking about that while I was doing it. Wow, it's kind of silly to build an open website where anyone can look at my sleep patterns. So you can do this in a couple ways. The Bluetooth connection is actually very insecure because you just need to know the 4-digit code in order to read the data off of it. So I'm not sure if there's a solution to make Bluetooth more secure, but for the website, you would just build a login system, right? So you would just require a username and password to be able to view the data.
So one thing I mentioned is that this device also works just over Wi-Fi outside of a wired connection. And the prototyping platform I'm using to do the Wi-Fi, I was really impressed to see, does all of their connections over an encrypted channel. So actually, by design, the platform is pretty secure.
Let me comment on that as well. I mean, I think both answers get to one of the core issues here, which is that when people build these devices, they tend to use the commodity technologies, whatever they are, which is one of the reasons it's important that those commodity technologies actually have security built in, rather than being something that you add on, that's added on just by those who need it, right? So there ought to be secure communication facilities between the Arduino and other things. These Wi-Fi devices ought to be more uniformly like the one that Dale talked about, which does offer privacy by default. But right, a lot of that is about the enabling technologies being there, and also people being trained to use them.
So I'm wondering, Bonnie and Dale, if you guys could describe a couple of your previous projects and then what your next project is going to be.
Sure. So I guess previous projects, I did a piano stairs installation at Princeton last fall.
Explain what that is.
Yeah, so piano stairs. So I basically hacked a staircase. You couldn't really tell when you walked down it, but each, not visually, each stair was keyed to a different note that I had, and I had a computer and some speakers at the bottom that were playing those notes. So people would walk down the stairs and discover that they were actually a piano. That was fun. I've done some more musical stuff. Last week, I turned a mug of water into a musical instrument for a class project. And then, one of my fun ones from last spring was we built a bookshelf that would keep track of which books were on it and would give you a web interface into that. And my next project is actually a 50 square foot wall of LEDs that are going to light up when you hit them with water. So we're working on that.
Be really cool. So a few projects I've worked on in the past. Let's see, my friends and I made this device. It has like a gyroscope and accelerometer, and it's a Bluetooth thing. And we sort of made a glove of it where you sort of move your hand and it modulates music in some weird way. So that was kind of cool. And then we got a bunch of these Bluetooth devices with all these sensors in them that were really small, like this big, and $20. And so we put them in a bunch of things that were related to us doing tasks. So for example, we put one of these tags in our gym bag, so whenever we went to the gym, it would be logged automatically. So yeah, the idea was that we wouldn't even have to like mark when we did tasks.
It could be automatically nagged if you didn't go.
Exactly, yeah, definitely. And future projects, I've been working on something with the Raspberry Pi about forever, but I keep on adding and removing features, so it's never gonna get done. But basically, it's going to be sort of a music streaming platform for me to stream from Pandora or Spotify or my phone and have some LED visualizations. So, yeah.
Oh, I forgot one. I'm also working on a brake light backpack. That's actually taken from Adafruit's website, but it's essentially a backpack where the lights automatically light up as you're braking on your bicycle. So.
Hello? Oh, thanks. Very great projects, very cool. Thanks for coming. I think we talked a little bit about some of the security features. I'm sure the rest of the day we're going to be talking a lot about some of the privacy implications of creating all this data. And since you are the folks that are going to be building all these cool things in the future, I'm wondering how much thought or discussion goes into your projects around the question of how much data is this thing generating. Is that something you think about as you're designing it? Is that part of the education you're getting around building these things? Just thinking about how much data is being created and is it all necessary to the functionality of the device?
Yeah, so that's a great question. I think there's definitely a sense on campus that a lot of people are really concerned about that. It's definitely a hot topic. I think most people, when they're designing new devices, new projects, are thinking about that. Part of it is that, though, we're only building devices for our personal use. So even if people are discussing it, it doesn't necessarily get implemented. I guess people are more willing to expose their own data than other people's, which is probably good. Do you have any other thoughts?
I don't really have that much to say, but I will say that, like, as Professor Felten said earlier, it's a good idea that sort of like prototyping platforms maybe have some sort of thought put into this when you begin prototyping, because as a student, a lot of times you're sort of like, I just want this thing to work. I want it to track everything. As long as I get something, it'll be great. So, a lot of times I'm not thinking about it.
Sounds like a lot of fun. Good work. Have you thought about teaching a sensor that is you who's using the pillow and not somebody else?
Can you repeat the question?
Identification question.
Oh.
Because privacy and identification are very strongly connected.
Mm-hmm.
Have you thought about how to train your sensors so that when you're using the pillow, it knows it's you and not somebody else?
I hadn't actually thought about that. That's a great idea. I guess you could do that in a couple ways. You could assume that whoever has my phone is me, or at least until I report my phone is stolen. And you could very easily figure out, okay, is the phone next to the bed? I don't think with the sensors I currently have, I would have enough information to identify people. One thing I was thinking about was actually turning this from a pillow into like your bed sheets, right? Then you'd get full body tracking and you would be able to figure out if it was the person.
Well, thanks very much. Let's adjourn, and we have tables in the back. Yes, so if you want to come see the projects up close, I guess these guys will be at the tables in the back. Thanks very much.
So we'll start the next panel in just about 5 minutes if the folks for the security session want to come forward. But I think that was a really fascinating way of kind of getting us into what these things are that we're going to be talking about. And some of the displays that we just saw, I think we'll find later throughout the day will clearly be linking to specific conversations that the panelists had. So I really thank the two students Dale and Bonnie, for giving the presentations. It's really amazing to think that projects that are done in just a couple of hours for between 20, I think the most expensive was about $30 for these projects. When we think about that and think about the implications that's going to have for how many of these kinds of daily life connected technologies we'll see in the future, it's really kind of striking. Okay.